screen? Awesome, thank you. All right, welcome back, everyone. So today we're going to talk about, cover two chapters in this section of the book that seems to address, let's say, common problems in data visualization. First chapter is going to talk about the problem of overplotting. Basically, when you have too many points and those points in the graph are, as the name suggests, plotted on top of one another such that you can't necessarily see any pattern. Can't see the forest for the trees, as the metaphor would go. And then the second problem is going to concern color and some of the disparate problems that can come from usage of color, using too many colors, using the wrong colors, and using colors in a way that's not mindful of color perceptual issues. So I'll start with overplotting. And I think maybe the best way to start is if you're not familiar with this term, is just to start with a graph. And sorry, one point. Forgive me, this week I didn't have time to make slides. However, I did read through the chapter, feel ready to discuss. So I'm just going to walk us through the chapter. Probably my slides would have just been Klaus's figures in any event. So maybe you're not losing too much for my lack of preparedness. But overplotting also suggests can come from a few different sources. One would be where we simply have too many data points, and naturally, if you have lots of data points, they may overlap one another if plotted into some kind of a two-dimensional plotting space. Another would be where the data have been transformed and there's some rounding such that you find yourself with lots of points that have the same value just because of the way in which data points were computed. So in this case here, we're looking at something related to fuel economy, so miles per gallon. So you have the number of miles you can get divided by the number of gallons. And then this is rounded, if memory serves, to the first decimal place. So you can see lots of values that are exactly 2. And these values kind of aren't continuous, but there's some, like, let's see, discrete jumps at the kind of for each tenth of a value, and we end up having lots of overplotting. One data point I want to draw your attention to that's kind of subtle, and I just noted it. Okay, maybe I can't zoom too much more, but this data point right here, hopefully you can kind of discern it when my cursor is going around. So we're somewhere about 2.5 or something like that. This third data point from the top, you see yellow, and there's a little bit of a faint halo of black around it. The reason being that there are 2 points right here. There's a yellow point that is overplotting, that finds itself almost exactly on top of the black, such that there's only a very subtle hint that there's a black point that is underneath that. So that's the problem that we're facing. And when you have this overplotting, you can effectively end up hiding some of your data points by different layers of data. You can imagine that maybe the black ones are plotted first, then the blue, then the yellow, then so that you'll have these yellow spots, these yellow points that would end up hiding data points of a different color, and so you won't be able to recognize the patterns here. So the author suggests a few solutions to this general problem of overplotting. The first one is one that probably many of us have used. It's kind of a 1-2 punch of jittering and transparency. So we'll look at the transparency first. So we can kind of improve this plot, this previous plot, where you have very full saturated colors, by introducing a level of transparency. So in that way, if we make points transparent, we can actually see that, back to our little favorite data point right here, it's rather dark, and we can see that there's actually a black data point behind it. Something that we couldn't see before, except that I kind of gave you a few little hints of pixels that were maybe out on the outer edge. So we can see here immediately this has been an improved graph, so we can see where the darker points are ones where there's some overlap. So you have this very dark blue because there's a black data point, I think, behind it. You have this kind of blackish yellow data point because there's a black data point behind it. So already we can see the multiple layers of data, even in cases where one data point completely obscures another data point. So this opacity helps us already. But the problem is, we can see, yes, that some data points are darker or lighter than others, but we may not always be able to easily discern which data points are covering which other data points. Like right here, I have this yellow that's kind of verging on gray. What's behind it? Is it black? Is it blue? I don't know, right? So it's kind of unclear here. Also, for the untrained eye, so for people that aren't familiar with opacity, changing opacity, even though there's a scale right here, a legend within the plot, we may wonder what these different colors of points mean, right? Because we've read the chapter, we have some sense of what they mean, that the darker points correspond to ones where, two or more points are at the same X and Y coordinate, and are overlaying one another. But to an untrained eye, or to a reader who's not familiar with this kind of problem and the solution to this problem, partial solution to this problem, they may wonder if these are actually different kinds of data points, right? These very black points, some variety of four-wheel drive that's a darker hue than the hue that's given to the four-wheel drive. So one way that we can further improve this is through the combination. So the first author suggests that we can do transparency and jittering. So far we've just looked at transparency and how transparency alone, introducing some level of transparency into the data points, can already improve our overplotting problem. But it's even better still when paired with jittering. So jittering means that we introduce some random noise about the placement of the actual points. It's a little hard to see we can't see these side by side, but basically we can have some jittering. We can say, let there be some random noise in either the X or Y, or maybe both dimensions. So in effect, we're moving the points slightly from where the points actually are. So if I have, oops, sorry. Pressed my keyboard, my finger brushed the keyboard at the wrong spot. So some of these points are appearing on the plot at a different coordinate than they actually are in the data. And so we're displacing these points by some small little disturbance term, so that we reduce this overplotting, or simply randomly moving the points. And indeed, we can see already that there are some black points over here in this part of the graph that weren't immediately visible in previous iterations, right? But of course, following this trend, this solution, when exercised without a lot of care, can engender still another problem that I hinted at earlier, is that we could effectively have the visualization be kind of a deformed version of the data itself. So if we jitter the points too much, if we randomly move them too much, we end up with a plot that doesn't actually represent the data. So actually, if we look back at, see these black plots right here, I think there are these black plots points right here. They just got moved all the way over here because we had a very large jitter. So we end up seeing a trend here in the data with the black plots that may not exist in actuality if we looked at the data. So we can kind of address this problem of overplotting through introducing transparency, so that we can see when there are a good number of points stacked on top of one another. We can further improve it by introducing a jitter, so some strategic small displacement of points in either the X and or Y axes. But we have to be careful with both things, right? We have to exercise some care, particularly with the jitter, because we're actually, as I mentioned earlier, by introducing some random noise in the placement of the data points relative to the data actually in the source data set, we may end up, how do you call it, creating a plot that that doesn't really represent the data itself, where we're introducing some, just by chance, random chance, some random patterns that don't actually exist in the data. So we have to exercise care. I think probably the takeaway here is jitter, but jitter very little, or relatively little. If we do it too much, we could end up causing more problems than we solve. Yeah, and then I forget whether the author goes into this point here, but there's no visual asset that corresponds to it. But also, when we introduce the transparency, one potential problem that we could have is that if we make points too transparent, some of them may be difficult to see, to perceive, right? So if we have a starting point, at the starting point, this is a very pronounced yellow. If we make it more transparent, it becomes more faint. Imagine that we made it still more transparent. Against a white background, it might be difficult to perceive in cases where data points are single data points kind of off out into an area that's relatively unpopulated. So again, we have to be careful about how we introduce transparency so that we kind of solve a problem without creating further problems. Yeah. Let me stop here, I guess, and see if there are any comments or questions on this point so far.
Not from me. I wonder if there is, I don't think the author includes that in the chapter, but if there are any recommendations on when you're doing transparency, which color palettes to use in order to avoid, for example, if you do like primary colors, let's say red, yellow, and blue. And then when they are on top of each other, then they can look like green or like purple or something like that. So I
Oh,
wonder
that's a good point.
if there are recommendations when it comes to that. I guess just use like a normal regular palette that already has been created, but in case people want to get creative or something, I've never seen anything on that, but it just occurred to me because all the things you were saying about the transparency colors, right? But yeah, something to keep in mind, I guess.
Yeah, exactly. That's a very sorry, I thought I'd remuted myself. That's a very good point, Gabby. I feel like that might be one of those parts where data visualizations are sort of iterative, right? It might be hard kind of ex ante to make a decision about the color palette, but you might kind of see something and realize that for your particular data, that a strategy that is in general good may not work out for your particular plot because of this, kind of when colors are overlaid on one another, maybe they generate or appear to generate a new color. Or you could have, over areas of overplotting with two colors that maybe give the indication that it's actually a third level of color, right? Yeah, that's actually a valid level in your data set. That would be even a worse problem potentially. So sticking in this theme with overplotting, so the author has kind of three ways to think, three tactics for addressing this problem. This is tactic number one, a combo of transparency and jitter. Tactic number two is what he calls 2D histograms. I'm not sure I'd ever heard this term before. This is kind of an interesting part of the chapter for me. Here, we're plotting flight departure times. So this is the departure time on x-axis. So when the flight leaves, or if it's scheduled to be left or actually leaves, I forget which. And then the delay in minutes, right? So here we can kind of see it's just a really thick mess of points. It's a little hard to discern patterns. You can see that there are lots of flights in this area. But because of the extent of the overplotting, it's difficult to gauge, apart from maybe these areas, whether there's like a gradient in the number of points, as we approach this axis here, like the zero, or if like what's the kind of like density plot, if you will, and of sort of like this area of the plot. It looks very black, and it's really hard to discern what patterns there are, if any, in the data. And to combat that, the author prescribes that basically what we can do is it's almost kind of like a heat map meets scatter plot, if you will. So what we do here is we kind of have this really nice thing where we have the number of departures, and then we have things plotted here. And so in effect, it's kind of like rather than points, we have a box, and then the darker the color of the box, the more flights that fall into that data point. And so with this one change, it makes it really clear. Well, a few patterns emerge very clearly. Number one, that most, well, if you like flights are between, let's say 6 a.m. until, I don't know, maybe 1900 hours or something like that. So that's when most flights are, it seems. And then also most flights are on time, or mostly on time. But we have a very long tail of flights that are considerably delayed, right? Um, that wasn't obvious from, it was very hard to see that pattern here. In fact, I'd say it's impossible to see that pattern here because of the extent of overplotting. Here, this is the case where we have lots and lots of data points, and just by putting them in plotting space, we end up having lots of overplotting, and it's hard to see the pattern, any pattern of interest. So this is kind of interesting. It's almost like, again, it feels like a marriage between a heat map and a scatter plot. I don't know that I'd ever seen this before, and this is kind of a nice way of doing things. And he suggests still another improvement, which is, I think, a modest improvement by my lights, is to, rather than using squares as kind of to represent points, instead make hexagons. So the what this gets us is that with the utilization of hexagons, that the, how to put it, it reduces, I guess, the distance between the actual underlying point and the area that represents the point. So the squares are kind of bigger, and this is like kind of more like a circle, if you will. It's still square and well, I shouldn't say square. It has hard edges, and you can kind of like each, if you imagine the point of the sensor, like the distance to the outer edge is less with this shape than it is with this shape. Is what I took from it. But I think that's probably a small point. At least that's what I took from this. I don't know if others got anything else from this section, but it was an interesting exercise and interesting problem, where here we had drastic overplotting, and we were able to reduce that here. Here, I guess, like one other thing that goes unspoken a little bit is these are just plots. These are just points, coordinates. And here we're actually looking at kind of it's here, like the points. There's also a way in which we're encoding the number of observations that fall within an area, if you will. Whereas here we're relying on kind of the blackness, the darkness of the area to convey that same information. So really, I guess, in a way, we're kind of reframing. I don't know how to put it, but let's say, like, reframing the problem to sidestep the overplotting issue. Pretty clever, I thought. Third strategy, which I kind of feel like for me in this chapter is a progression from familiar to unfamiliar. So jitter and transparency was very familiar to me. That's the thing that I reach for when I face this problem. I had not found a problem where this solution was novel to me, but it immediately made sense to me when I saw it. This third one, at the risk of kind of poisoning the well, so to speak, was to me like unusual, both in the sense that it's a novel, and I felt like it didn't quite do, it didn't scratch the itch of being immediately interpretable in the same way as the others did. But here, like keeping with this idea of almost like having a density plot for here is using contour lines to basically come up with groups of where there's like a certain number of points here. And so here you can see that there's a large cluster of points within this circle, another kind of arbitrary grouping, so on and so forth. And the ideas, I guess, is sort of like topological in a certain sense, where you're showing like, I guess you're aiming to kind of show density graph by just encircling areas within these contour lines that capture a certain number of points. I've never done this before. I feel like I'm doing a very poor job of describing it. But this maybe doesn't look great at the outset. You have these really dark lines, but it's kind of hard to discern like what's going on here. I can see, yes, there are lots of plots. I can see, yes, there are contour lines, but it's a little hard to interpret. And one thing that we can do that makes this a little bit easier on the eyes at the very least, is to color the areas so that these areas kind of naturally show, like the darker the color of the area within the contour lines, the greater the density of points present. So here I can see that, the biggest mass of points is here, next biggest is here, and then kind of going out from that point, I can see there are lesser and less, like fewer and fewer points within these contour lines. So this is one case where, maybe we would have a bunch of points. We just want to see, where do most of the points fall. But maybe we could subdivide the data into different groups. I believe this is the Palmer's ping. Oh no, sorry, this is Blue Jays data set, not Palmer pings. Blue Jays. So here we could kind of have two overlapping groups. So we could say female birds. So these are contour lines for female birds represented with the orange, and these are contour lines for male birds represented with blue. To me, it seems quite busy. I can kind of see what's going on, but visually it's quite busy, and for that reason, a little hard to really immediately see any pattern without concentrating. And so the author kind of suggests, well, the author suggests a different solution later on, but uses a different data set to demonstrate this nicely. Is here we have the famous diamonds data set, where we're looking at price as a function of carats, and then the color dimension right here shows the quality of the stone. Fair, good, very good, premium, ideal. You can see some binning, I guess, of observations, but it doesn't really, not many things jump out. If we do contour lines with this, then just like with our Blue Jay example, it's kind of a mess. You can kind of see some groupings a little bit, but still it really seems like perceptually it's quite a mess. But this can be solved with one simple solution that I think we equally could have applied to Blue Jays, and that is faceting, right? So we can look at each group on its own. So we can take all diamonds of fair quality and produce contour lines, as we've seen before for the diamonds of fair quality, good, very good, etc. And here you can start to see, within these groupings, patterns emerge, at least where you can see more of the density. You can see where more of the density is located in kind of this space of prices versus number of carats. Yep. So I thought that was a kind of nice thing. I'm not sure if I'm going to reach for this anytime soon. Interesting discussion. I'd actually be curious to hear if anyone has actually used this before, and in what cases. Because this is, again, to me, I feel like this chapter progressed from most familiar to least familiar, and this was very unfamiliar to me. Like first the usage of contour lines, and then kind of trying to do it for these cases. Has anyone used contour lines before? Curious.
So
I have not.
you haven't read? Yeah, me neither.
I've just seen them really, but I've never had like a use for them in my own work.
Yeah, so I've only seen them done or in papers. I do remember way back when I was doing some multivariate analysis and models that they had a function called orDsurf, and essentially it would do something like this and group them by density. But I don't remember exactly a lot about that, but so I've only seen it theoretically used. One thing that I was gonna say is that I think that these contour lines make more sense when they have color added, because then you can see, like in the example that was before, with the peak length and the weight, I guess. Yeah, that one. Then you know that the center, it's sort of more like more intuitive to understand that in the center you have the majority of the density, or it's like the most dense part, as opposed to like the areas on the periphery. And I guess that's how these lines are interpreted, but I guess it makes it more intuitive so that people are like, what are those lines, right? Like sometimes it's not as intuitive as that one. And the other thing that I was going to add is, so yeah, if you're going to do contour lines, do color and make sure that that is in the caption in some way so that your audience sort of like follows you with the contour lines. And then the second thing I was going to say is that I liked the other graph that was talking about the males and females with big length and weight, or body mass, or head length. It was not big length. So I do like it because you're comparing two groups, but I know that because there's so much overlap between them. So what you can do is, if you want to highlight females, put males in gray, in a very light gray. That way they're there and you can sort of see that, oh, well, females have like a wide variety of weight or body mass versus males, they don't have that much variation. And definitely males are going to have a larger or a longer head length versus females, so that you can sort of do those comparisons, right? But yeah, highlight one with color and then the other one with gray so that it's like faded in the background. But yeah, those are just my two cents here on these parts.
Yeah, I'm in the office today and don't have my video, but I was nodding my head vigorously, Gabby, when I was hearing you saying, it was like basically, you know, focus on one and have it in color and have the other in something that's in the background, so it's present, and you can kind of see, in this case, how female birds differ, like kind of their distribution differs from that of male birds in this case. I think that would be a really nice way of doing things. Yeah. And I think you're right on this point too, Gabby. I think I guess the author doesn't include any kind of any guide for the reader in the plot itself, because it's in the context of a book that's explaining the plot. But if the plot were provided in isolation, I think one would maybe not even need to explain these contour lines, because I feel like these are not often used. And you'd have to say, like, the darker the area, the greater the mass of points present, and even that probably wouldn't resonate with a large audience, maybe more of an academic audience. Anyway, yeah, so these are the three strategies for overplotting. You know, again, jitter plus transparency, that's strategy one. Strategy number two is what the author called 2D histograms. Yeah, 2D histograms. And then the last one is contour lines. Those last two are new to me. All right, so moving on to our second collection of problems, color. So here, you know, whereas in the last chapter, it seems like the common thread was over plotting. Here, I think the thematic, the common thread is a lot, doesn't tie the topics together quite as well. I think it's just like there are multiple problems you can have with color. And so one is that, you know, you can use color for too much, and I think this is the author puts here bad. I feel like if I were writing this book, I would just write no. Don't do this, because I mean, this is really awful to have all of these hues that are meant to represent, you know, each one representing an American state. There are 50 states here, and as many colors, many of which are, as you can see here, very, very similar, such that it's very difficult to discern the difference between any number of them. You know, Indiana and New York, one is darker than the other, but I would be hard pressed to identify Indiana or New York in this plot. So this is asking color to do too much. And one solution the author picks is to use fewer colors. And I guess implicitly encode encode data in a different way. So this previous plot, I think the data points are exactly the same, or almost exactly the same. Population, and then population by population growth. Here it's a lot easier to see what's going on because the author, rather than coloring each individual American state, each one of the 50 individual American states with its own unique color, instead the author has grouped states by region. And I guess these are the census regions. I'm not sure. I guess if I can find Maryland here, if it's in the South, then it's census regions. You can see here, like we went from having 50 colors to having only 4. But so that you can know which states are which, some of them are annotated. And now I don't remember this author went into how one would want to go about annotating these things, and I guess a lot would depend on what story or stories you would want to tell about the states. Like, here you could have maybe large states that are growing quickly, Texas. You could have small states that aren't growing much at all, Vermont. And you could highlight those individually if there's a story you want to tell. But here, I think you achieve the goal of being able to show all of the states in one plot, and then be able to kind of see maybe some information about them. But of course, it's not perfect. You have to give up on the theoretical ability to uniquely identify each state by color, theoretical, for having some kind of practical strategy where you use fewer colors. So I guess lesson, don't use too many colors, use other strategies, other complementary strategies for identifying your data points. Also, another problem of using too many colors, and this is really hard to look at. I feel like this is another one where I would write no. Is here encoding things with colors for no good reason. Here, the idea, I guess, presumably, is to make it look pretty somehow and follow rainbow colors, but the colors add no value to the data, right? And indeed, they may even confuse, because you might think, well, these blue colored states, do they have something in common? No, we're just arbitrarily, we have a color, we have a kind of words escape me now, but we have kind of a set of colors ranging from this red all the way to this orange, and we're just kind of going along a path, and I guess having an n number of states with those colors. The color does nothing here, and the author says, instead, in these cases, use colors to convey meaning, right? Instead, so maybe you might want to highlight Nevada, or if you're telling a story about a particular state, maybe you look at Tennessee for whatever reason, and you would have everything else be gray, perhaps, and then Tennessee be a color. So Gabby's strategy from earlier. But don't use, there's gonna be too many knots here, but don't use, well, let's see, don't use colors gratuitously, right? Use colors as a way of encoding information about data. Second problem with colors is if you have color scales, right? That was the word that escaped me earlier. If you have scales, don't use non-monotonic scales. So meaning, he picks on this rainbow scale. It says lots of people like to use this rainbow scale. But if you were to plot data on a chart, so monotonic would be kind of like increasing and increasing or decreasing. So you should be able to tell from the colors that a value is bigger or smaller than another value if you're using color to say something about the quantity of the data point. So if I were to plot pink and green, I would be hard pressed to say which is bigger. There's nothing about the scale that tells me that one thing is bigger than the other. And even when you convert this same scale to grayscale, it doesn't give you any more information. Here's a case right here. If you look at the map without without this key, what is it telling you? That there are just lots of colors. It's very difficult to say what the colors are meaning to convey without reading this. And even with reading this, it's you have to kind of encode this odd scale in your head in order to interpret this map. So instead, it would be better if you had, maybe I'm just going to make up something. Instead, you had a scale of blues, and you had darker blues have bigger quantities, and lighter blues have lesser quantities. And then you would have a scale that ranges, between those two, or maybe if this were a American political map, then it would be colors that range between blue and red, kind of the colors of the two biggest political parties in the United States. Then, that would mean something for readers in that context that about kind of the percentage of votes for particular parties. Okay, so don't use non-monotonic color scales to encode data. Last problem that the author points out in this chapter is when you're using colors, think about people that may have problems with color perception. So there is a small but not insignificant proportion of the population that has color blindness of some sort. So an inability to discern between different hues of color. Why does that matter? That matters because if you're using color gradients or other kinds of, if you're mapping data values to color, if it turns out that those let's say two or three colors are not perceptually different for the person viewing the plot, then your encoding of data with color is useless for that population. Or even if you don't, and I think the author doesn't talk about this, but this is something I've thought about a bit recently, is even if you don't care about people with color blindness as an audience for your plots, think about grayscale. If people print your plot in black and white, will your carefully chosen color scale still show the same information, perceptually the same information if printed in black and white? Yeah, that's something to think about. So to see this, like the difference in perceptual colors is, on the have a look at the scale. Here you have an original color scale that kind of goes from this dark burgundy red to kind of the light to grayish yellow. These are the major. I think there are other categories of color blindness, but you can see the differences in how people perceive this color scale. To a degree, it kind of still works across all groups. But you can see that the way in which it's perceived is very different. So if you have no color blindness, then you'll be able to discern the differences. If you do, then maybe this will look different for you. And so you can think about that for individual color scales, or if you choose a set of categorical colors to represent categorical values within your data, think about these differences. Red and green color blindness is fairly common. And it can really transform some of our plots, our designs here. So, for example, if you can't discern the difference, if a viewer can't discern the difference between red and green, then your kind of red to green plot, maybe this is one extreme, this is another extreme, these are intermediary values. Look how this looks for them. The two poles look exactly the same. So if you choose this plot, you will have completely failed in conveying your point when encoding color if some members of your audience have any kind of difficulty with color perception, certain types of color perception. So this is maybe the most extreme case, but you can see how it plays out for others as well. Yeah. I wanted to point to a couple resources that I found kind of really quickly that I kind of tried to use in some work that I was starting. And I can drop these resources in chat if you deem them useful. One, which I was really surprised didn't make the cut in terms of references, or maybe I just didn't see in the references, is this package called Color Space. I was surprised it wasn't there because you'll notice a familiar name among the developers. And what's nice about this is I think you can basically set your color palette, and then you can see how that color palette would work for people with different different problems in color perception, right? So there's a whole vignette on this. So you can emulate that case and see if your color palette is robust for those things. A couple other tools I found outside of this is one. I don't even know who made this, but I'd used. So you can kind of. I'd wanted to make a blue scale here, and I had lots of concerns about, well, number one, for people with no problems with color perception, can you even, are the colors perceptually different enough? And then if I wanted to emulate different color blindness, I could click along the top and see, and then these will change, and I can kind of discern whether differences in elements of my scale are still perceptually different. And then along the bottom, you'll have some comments about these colors and the extent to which they're still perceptually different. Yeah, so this is kind of a nice thing, and you can drop your own hex codes. So these are I don't know if it accepts all. Yeah, okay, yeah, it accepts hex, RGB, and HSL. I was working with hex codes. Yeah, you can do the same thing with other kinds of scales. Yeah, that's I think all that I've got. Sorry that it was just a little talk through of the chapter, but I didn't have time this week for slides.
No, it's okay. Thank you, Arthur. And these resources look amazing. So just drop them off in the chat.
Sure.
So that we can have them. Because I don't know if you guys know this, but at the end, when the whole not the whole chapter, but the whole cohort is like compilated, or I guess compilated is the right word. It includes not just the video in the like in the final, what is it called? It's not a markdown. Well, I guess it's still a markdown document with all our notes. It also has at the end of each chapter the video and our chat
text. Okay, cool.
Yeah, everything that we write there. So they are, all our comments are preserved for forever and ever, because Slack deletes them after 30 days, I think. So
Right.
it's always good to put these kinds of resources on because they eventually will end up in the final document, right?
Awesome.
So, so yeah, this was really good. Thank you so much, Arthur. And no worries about the slides. I mean, they are highly encouraged, and it's something that John always says, but sometimes life gets in the way, and we get it, right? So no worries about that.
Yeah, one other thing that I guess I thought was kind of funny. I was trying to design a ggplot package for some stuff internally at work, and I looked to a few of the exemplars. One of them was Urban Institute, a think tank in Washington, D.C. I think they're a think tank. And they have their own nice style guide, and you'll see that they have colors, and these are drawn kind of from their own kind of branding guidelines, different colors for different number of categorical groups. They have different scales, so on and so forth, 4 categories. They'll have sequential and categorical things for 5, 6, 7, and then my favorite right here, that's 8. This is too much. So this is kind of back to the author's point within the chapter, is that really, if you're using more than, I don't know, here Urban would say more than 7. I might even stop it earlier than that. But if you're using more than a certain number of colors, strongly consider a different way of encoding with color. Maybe not at all, or maybe making groups, as the author did with the American states.
Yeah, I think I always have thought that between 6 and 8 is like the sweet spot. No more than 8, definitely. But I've seen crazy things online. So yeah, I think that's a good reminder that we should just keep it concise, especially because of all the things that we talked about in the end about people having like color blindness and all of that. And it's also like how much can you really differentiate, even if you don't have those issues, those color perception issues? I don't know if that's an issue, but things. It also at one point it becomes like it's too much. How many groups can I really hold on in my brain, and then like, do I want to compare among them? So yeah, I think that's a very good reminder. Thank you so much, Arthur.
Yeah, I mean, just one point on that, Gabby, that sprang to mind is you know, I think like oftentimes like these let's say like accessibility guidelines, I think that's what people often call them.
Mhm.
Is I feel like what people don't say enough is I think, you know, certainly they're meant to address some difficulties in accessing certain documents for certain populations, but I think very often, in fact, even more often than not, like those changes that are made to accommodate, let's say, people with certain difficulties actually end up improving the thing for everyone. And
Yeah,
so I don't know that this is universally the case for color, but I think oftentimes when colors are close, you know, too close, they may be even too close to be perceptually distinct for people without any vision difficulties. And having to think, you know, if only having to think about these problems might lead you to better color choices for everyone. Yeah.
I love that final comment. Perfect way to end this chapter. Thank you for that, Arthur. Yeah, I agree with you. 10,000%. All right, so if anybody else has any comments or things that they would like to discuss, I personally can talk about color. You don't understand, all day, every day. I love all this color theory and everything. I even have a color package that I started. Oh my God, I think last year, I started it last year, I think. And I need to just sit down and finish it because it's almost done, but I need to put it like in a package or something. But anyway, it's very simple, but I think it's from a series that I think a lot of us like. But anyway, so yeah, I think this was a very cool 2 chapters which deal with very common issues. And I think it brings us to consider these common issues in a different light, or in a different way that we are traditionally that we usually see them, or that we commonly see them. So I think I like that. I like that about these 2 chapters. This book overall has been very, in a way, simple, and some chapters could be improved, I guess. But there's always something in each chapter that I'm like, oh, I haven't thought about that. So it's like a few nuggets here and there that you're like, yeah, I mean, it's just one, but it's a good one. So I've been enjoying this book a lot. So for next week, you guys, we don't have anyone presenting. So if you're interested in that, it's going to be chapters 20 and 21. I don't remember what those are. Yes, thank you. Redundant coding, which I don't even know what that is about. And then multi-panel figures, which that's a lot of fun. We all love doing multi-panel figures, like the one with the areas, what do we call that? With the contour areas. So if anybody's interested, if nobody signs up, I will present it, because that's like what I do as a, what do you call it, chapter organizer or whatever. So so yeah, I'll keep an eye out if anybody's interested in presenting those 2 chapters. And I guess that's it, you guys. Have a lovely weekend, and we'll see each other next week.
Bye-bye.
Perfect.
Thank you so
Thank
much.
you so
Arthur.
much.
Thank you, Arthur, for such a great chapter. Well, 2 chapters actually. So thank you.
My pleasure.
Yeah, thank you so
See
much.
you guys again next week.
Bye-bye.
Bye-bye.